All right, question 47. This is actually my second attempt at question 47. Here was my original solutions to question 47. Ended up getting answer C, but as you can see, the work got a little bit ugly down here. Some of the arithmetic was a little bit annoying for a test where you're not allowed calculators. I think in the video I even talked about how I bet there's a clever solution that makes things work out a little bit more cleanly than this method of parameterization that I used. Well, sure enough there was, and fortunately somebody pointed out in the comments. So big thanks to this arbitrary person with their arbitrary handle down here. So I think what I'm going to do is start this video by re-solving question 47 using that method suggested in the comments, but then append the video that I already made using this parameterization method, because I think it's beneficial to see both ways to solve the problem. In this specific case, this method may not have been optimal, but in a similar problem you might have to do a method like this, so it's good to go over. Anyways, the trick for the clever solution to question 47 is to employ a theorem that I actually talked about a couple videos later. Looks like it's question 49 here, where I mentioned this thing called the Cauchy integral theorem. And what that tells you is that the integral over some closed curve C of some function f of z is just equal to 0 as long as that function is kind of well behaved inside C. Holomorphic being the technical description of well behaved. So what that tells us for question 47 is that if instead of considering this integral on the straight path from 2, 0 to 0, 3, we instead consider the integral on the closed curve made up by this triangle. So maybe from 0, 3 to 0, 0 to 2, 0 back up to 0, 3. The Cauchy integral theorem tells us that that integral must be equal to 0. What I'm saying is that 0 is equal to maybe the line integral on A, or this is A from 0, 3 to 0, 0, plus the line integral from 0, 0 to 2, 0, maybe the line integral on B, if we call this B, plus the value of this line integral on C that's referenced in the problem. It might look like we've just made things a lot harder, but really we haven't, because when we're dealing with this line integral on A, you might know that the x value is always equal to 0, and therefore the change in x is equal to 0. So this first integral is going to simplify really nicely. This goes away, so all of this goes away. This goes away, so this whole term goes away. I'm left with just 8y dy to integrate as the y changes from 3 to 0. Similarly for this line integral in green, because I'm on the x-axis, the y-coordinate is always equal to 0, so the change in y is equal to 0. This whole thing goes away. This term goes away. I'm left with just the integral from 0 to 2 of 5x dx. We know that 0 is equal to the sum of these two integrals and the integral in question. So therefore, the integral in question is just equal to the negative of this integral, which we could account for by switching the bounds of integration. So the integral from 0 to 3 of 8y dy minus this integral, the integral from 0 to 2 of 5x dx. Conveniently, these integrals are really easy to evaluate. The integral from 0 to 3 of 8y dy is just 4y squared evaluated from 0 to 3. And the integral from 0 to 2 of 5x is just 5/2 x squared evaluated from 0 to 2. Over here I get what, 36 minus 0, so 36. Over here I get 5/2 times 4. 20/2, I guess that's 10 minus 0, so just 10. So I get 36 minus 10. In other words, 26 is the value of this integral. The answer is still C, but this method was a lot quicker and a lot easier than the method of parameterization that I originally used. As I mentioned at the start of this video, I think that method of parameterization is worth reviewing. So I'm going to append to this the video that I originally made solving question 47, where I used that method of parameterization. All right, question 47. Here we're calculating the value of a line integral. So we're integrating over C. C is the straight path in the xy plane from 2, 0 to 0, 3. So I think the easiest way to do this is to parameterize stuff. So kind of rewrite the x's and y's in terms of t, and then just integrate with respect to t. So there's lots of different ways you can parameterize, but probably the easiest is just to let t range from 0 to 1. Using this point for time 0 and this point for time 1, we know that the x-coordinate needs to go from 2 to 0, and the y-coordinate needs to go from 0 to 3. So if we write x and y linearly in terms of t, when t equals 0, x has to be equal to 2. That tells us that b is equal to 2 here, right? 0 plus 2 gives us this 2. And when t is 0, y is 0, therefore d must be equal to 0. When t is equal to 1, we need x to be equal to 0. So 0 must be equal to a times 1 plus 2. What I'm saying is that a must be equal to negative 2. Similarly, when t is equal to 1, y must be equal to 3. So 3 is equal to c times 1 plus 0. Looks like c is equal to 3. What I'm saying is one choice of parameterization, maybe the easiest choice of parameterization, would be to let x of t be equal to, what, negative 2t plus 2, and y of t to be equal to 3t plus 0, or just 3t. With these choices of parameterization, we can rewrite this integral. Note that if x is negative 2t plus 2, then dx is equal to negative 2 dt, and similarly dy is equal to 3 dt. We'll take these 4 pieces of information right here and substitute them into this integral. What that gives us is the integral from 0 to 1 of 5 times negative 2t plus 2 plus 3t cubed. All of that stuff needs to get multiplied by dx, which is negative 2 dt. To that we need to add 3xy squared, so 3 negative 2t plus 2, 3t squared, plus 8y, so 8 times 3t, all multiplied by dy, which is 3 dt. Ooh, what a mess. All that's left to do now is kind of simplify, I guess combine like terms. Is this something we can do in our head? Hopefully. Let's see. Negative 2 times 5 is negative 10. Negative 10 times negative 2t plus 2 is positive 20t minus 20. And then 3t cubed is 27t cubed. And when I multiply that 27t cubed by negative 2, I get negative 54t cubed. That wasn't so bad. What about over here? Well, 3t squared is 9t squared, and that 9t squared times this 3 and this 3 gives me 81t squared, and 81t squared times negative 2t plus 2 gives me what? Negative 162t cubed, I think, plus 162t squared. It's kind of the limit of my mental math. Coming over to the second term, this 3 times this 3 gives me 9t, times 8 gives me 72t. And kind of think about factoring out a dt, putting that at the end. Now if I combine like terms, kind of hope the numbers get a little smaller, although it doesn't look like they do. Negative 162 minus 54 more. Wow, I guess that's negative 216. Sure we can't use calculators here? That would be my coefficient on t cubed. Then I have this 162t squared. For my linear term, I got 72t and another 20t. So I guess I have 92t. And then finally, the constant of negative 20. All that's left to do now is take an antiderivative and plug in zeros and ones. This first term becomes t to the 4th power. Negative 216 divided by 4. Let's see, 200 divided by 4 is 50. And 16 divided by 4 is 4. So I guess this is negative 54t to the 4th. For 162t squared, the new exponent is 3. Divide 162 by 3. 150 divided by 3 is 50. 12 divided by 3 is 4. So I guess that works out nicely also. I got 54t cubed. For this next term, the new exponent is 2. 92 divided by 2 is just 46. And then finally, minus 20t. When I evaluate that thing from 0 to 1, what's nice is my choice of parameterization makes this really easy. When you plug in zeros, these all turn to 0. When you plug in ones, you get negative 54 plus 46 minus 20. So I get this sum minus 0 if you want. These cancel out. 46 minus 20 is just 26. Hopefully 26 is one of the answers. Sure enough it is. Answer C.